Welcome to class, everyone. I am so glad you're here. Today, we're going to jump right into a truly fascinating physical law, the law of thermal expansion. Throughout this explainer, we're going to put on our physics teacher hats and discover exactly why the physical world around us literally changes shape, growing and shrinking, just because of the temperature. So, let's start with something you've probably experienced right in your own kitchen. You know when you're wrestling with an incredibly tight, stubborn metal jar lid, and then you run it under some hot water and suddenly it magically loosens up? Or maybe you've been outside on a really hot summer day and noticed that the electric power lines overhead seem to be sagging way more than usual. Or if you've ever looked down at a railway track, you might have wondered why they leave those small, very intentional gaps between the massive steel rails. Well, it turns out all of these everyday observations are driven by the exact same scientific phenomenon. Okay, so what's actually going on here? If we look at the textbook definition, thermal expansion is simply the tendency of matter to change its dimensions, meaning its length, its area, or its volume due to a change in temperature. Basically, whenever a material is heated up or cooled down, its physical dimensions respond. It's an absolutely crucial concept that forms the backbone of thermodynamics and how we understand material properties. Here is our game plan for this explainer. First, the microscopic atomic view. Second, the math of expansion. Third, real-world engineering applications. And finally, number 4, common myths and mistakes. All right, kicking things off with part 1, the microscopic atomic view. Let's actually break down how this invisible mechanism works step by step. Step 1, energy, like heat from sunlight or that hot water on the jar lid, enters the material. Step 2, the atoms and particles inside that material gain kinetic energy, which just means they start vibrating a lot more rapidly. Step 3, because of all this intense vibration, the atoms spend more time further apart, increasing their average separation. And finally, step 4, when millions or really billions of atoms expand by these tiny microscopic amounts, they collectively produce a macroscopic expansion that we can actually measure. Honestly, a brilliant analogy for this is just imagining a bunch of people standing in a really crowded room. If everyone suddenly starts jumping around and dancing energetically, they naturally need more space, right? So the whole crowd just kind of has to spread out. Now, obviously, not all materials behave exactly the same way. Think about the states of matter. Solids are very closely packed. They're held together by strong attractive forces, so their expansion is pretty small. Liquids are moderately packed, so you get moderate expansion. But gas particles are already widely separated. They have tons of freedom to move. Because of that, heating causes gases to expand much, much more than tightly packed solids or liquids. Moving right along to part 2, the math of expansion. Let's look at the numbers. In the classic textbook equation for linear expansion, the increase in length, which we call delta L, depends on 3 specific things. It depends on the original length, L0, the change in temperature, delta T, and a unique material property called the coefficient of linear expansion, represented by the Greek letter alpha. So, long story short, a longer starting object or a bigger spike in temperature is going to give you a much greater expansion. The big takeaway here is that linear expansion is happening in just one dimension, just length, which, again, we represent mathematically with that coefficient alpha. But what if we're dealing with a flat surface, like a sheet of metal? Well, the math scales up beautifully for 2 dimensions. When a flat object is heated, it expands in both its length and its width. Because this expansion is happening in 2 perpendicular directions, the superficial or area expansion coefficient, known as beta, is approximately twice our original linear coefficient, alpha. This neat little approximation makes engineering calculations for metal plates and thin surfaces so much simpler. And naturally, we live in a 3D world, right? So the cubical expansion formula works exactly the same way. The change in volume, delta V, relies on the initial volume, the temperature change, and our 3D expansion coefficient, gamma. To round out this mathematical scaling concept, for uniform, isotropic solids, expansion happens along 3 mutually perpendicular directions. Therefore, the 3D volume expansion coefficient, gamma, is roughly 3 times our original linear coefficient, alpha. It's a really great trick. If an engineer only knows the 1D linear expansion rate of a certain material, they can just use this simple multiplier to accurately estimate how much a massive 3D storage tank or fuel container is going to expand. Which brings us nicely to section 3, real-world engineering applications. Getting this math right is literally make or break for engineers. Remember those railway tracks we talked about at the start? Engineers intentionally leave small expansion gaps between the steel rails for a very good reason. Without them, as soon as the weather gets hot, the rails would push against each other and violently buckle. It's the same for infrastructure. Long steel bridges actually use expansion joints and sliding bearings so the bridge can expand and contract safely without collapsing. Utility companies explicitly have to calculate for the summer sag of power lines due to heat. And, on a lighter note, heating the air inside a hot air balloon causes the gas to expand incredibly fast, making it less dense than the cooler air around it, which is exactly how the balloon rises. Ignoring these principles doesn't just result in a bad grade on a physics test, it causes cracked glass, snapped pipelines, and derailed trains. All right, bringing it home with Section 4, Common Myths and Mistakes. We need to clear up a massive misconception right now. A lot of people assume that objects somehow become heavier when they're heated. Total myth. The reality is that an object's mass remains exactly the same. Heat itself doesn't just magically add weight, and you're certainly not creating new particles out of thin air. Instead, that increased thermal energy is just causing the existing particles to vibrate harder and push each other further apart. The dimensions are changing, for sure, but the mass, that stays exactly the same. So before we wrap this explainer, here are your final exam pro tips to make sure you've truly mastered this. First off, always make sure you are converting your temperature differences correctly. Pay attention to those SI units. Second, do not confuse heat, which is transferred energy, with temperature, which is just the measure of average kinetic energy. Third, always identify if your problem is 1D length, 2D area, or 3D volume before you go picking your alpha, beta, or gamma formula. And finally, remember our crowded room analogy? Gases have way more freedom and are going to expand much more than tightly packed solids. I want to leave you with a completely mind-bending fact to take away from today's lesson. Did you know that the Eiffel Tower actually becomes several centimeters taller during the hot summer months? Yeah, it's true. That massive iron structure absorbs the intense summer heat, the iron atoms start vibrating with more energy, they push slightly further apart, and the entire iconic monument literally grows toward the sky. Pretty wild to think about the next time you're just trying to open a stubborn jar of pasta sauce. But it does leave us with one really important, provocative question to ponder. If massive iron towers grow in the summer heat, what exactly is happening to the vast amount of water in our Earth's oceans as global temperatures continue to rise? Definitely something to think about. Thanks for joining this explainer.